Hello everyone, and welcome to today's session. I'm excited to have you here as we dive into part 6 of our series, List, Tuple, Set, and Dictionary Operations. This presentation is focused on Python interview questions and answers for freshers. Over the next few slides, we'll explore key concepts, common questions, and helpful tips to prepare you for your interviews. Let's get started and make this session both informative and engaging. Let's start with dictionaries. To create a dictionary in Python, you can use curly braces with key-value pairs like this. For example, you might write dict, a equals 1, b equals 2, or use the curly braces syntax with key-value pairs such as 1, 2. Just remember, the keys need to be immutable types like strings or numbers. Moving on to sets, you also use curly braces, but this time with elements inside. For example, 1, 2, 3 creates a set, or you can use the set constructor like set 1, 2, 3. An important point is that an empty set isn't created with, because that actually makes an empty dictionary. Instead, you must use set to create an empty set. Now for tuples, the syntax involves parentheses like 1, 2, 3, or the tuple constructor. One key detail is that a single-element tuple needs a trailing comma, so 5 is correct, whereas 5 is just interpreted as a regular parentheses expression. Finally, lists can be created with square brackets like 1, 2, 3, or using the list constructor. For example, list 1, 2, 3. This flexibility allows you to choose the syntax that best fits your code style. So, in summary, understanding how to create these data structures, list, tuple, set, and dictionary, is fundamental for organizing data effectively in Python. They form the backbone of how we manage and manipulate data throughout our programs. Let's talk about how indexing works with lists and tuples. Negative indices are really handy because they count from the end of the list or tuple. For example, my list -1 gives us the last element, which is C in this case. Lists are mutable, meaning you can change their elements after creation. So you can assign a new value like my list1 equals X, and that will replace B with X. On the other hand, tuples are immutable, so trying to assign a new value to an index will raise an error. This difference is important to keep in mind when choosing between lists and tuples. Slicing works similarly for both lists and tuples. For example, my list1, 3, gives us a sublist containing the elements from index 1 up to, but not including index 3, which results in B. Remember, slices create new lists or tuples and do not modify the original data structures. And as an example, if we have my list equals A, printing my list 0 will output This highlights how indexing always starts at 0, making it straightforward to access elements directly. Let's walk through some common list methods using this example. First, we start with the list nums, which initially contains the numbers 3, 1, and 4. When we use nums append 2, we're adding the number 2 to the end of the list, resulting in 3, 1, 4, 2. Next, when we call nums sort, the list gets sorted in place, so now it becomes 1, 2, 3, 4. Then we use nums.pop to remove and return the last item in the list, which is 4. After popping that, the list is now 1, 2, 3, and the value 4 is stored in the variable val. Aside from this example, it's helpful to remember some key list methods. For instance, len, list, is a common function that tells us how many items are in a list. If you want to reverse the list in place, you can use reverse. And for sorting without modifying the original list, sorted is your friend. To find the position of an item, index X returns the first occurrence of X if you need to remove an item at a specific position. Pop I does that, removing and returning the item at index I to remove a specific value, remove. X deletes the first occurrence from the list, raising an error if X isn't found. Inserting new elements at a particular position is done with insert IX, shifting subsequent elements to the right. You can also extend the list by adding all elements from another iterable with extend iterable. And finally, appending at the end of the list is simple with append X. These methods are fundamental for managing and manipulating lists effectively. helping us write more flexible and efficient code. So to fully duplicate nested lists, you want to use copy, deep copy. Now let's look at an example. Suppose we have a list that contains a number and another list inside it. If we create a shallow copy of a using a slice, like b equals a with a colon, only the outer list is copied. Changing b's first element to 100 only affects b, but if we append to the inner list in b, it actually affects both a and b because the inner list is shared. This highlights an important point. A shallow copy copies the list structure itself, but not the nested objects inside it. So, if you want to duplicate everything, including nested lists, you need to use the copy module. You can import copy and then use copy for a shallow copy or copy, deep copy for a full deep copy. Alternatively, you can create a copy with list, or slicing, like b equals list of a or b equals a slice, but these methods only do shallow copies. Lastly, keep in mind that simply assigning one list to another, like b equals a, doesn't create a copy at all. It just makes b refer to the same list as to truly clone a list. You need to use one of these copying techniques. Now let's talk about slicing, which is a powerful way to create a new list that contains a subset of elements from an existing list. When we use slicing, we're essentially making a shallow copy of part of the list, meaning it copies the references to the elements, not the elements themselves. In the example, we have a list called nums with values from 0 to 5. When we do print nums1, 4, we're asking for elements starting from index 1 up to but not including index 4. So the result is 1, 2, 3. Notice how the stop index is exclusive, meaning it's not included in the slice. Similarly, print nums3 gets us the first 3 elements, starting from the beginning of the list up to index 3. Since the start defaults to 0, we don't need to specify it explicitly. When we do print nums3, we're starting at index 3 and going all the way to the end of the list. The stop index defaults to the end if we omit it. Now, what if we want to grab every other element? That's where the step parameter comes in. For example, print nums2 gives us elements at every second position, resulting in 0, 2, 4. And if we want to reverse the list, we can use a step of -1. So print nums -1 produces a reversed version, 5, 4, 3, 2, 1, 0. Remember, the syntax is always sequence start, stop, step, with start defaulting to 0, stop defaulting to the end, and step defaulting to 1. Slicing is a versatile tool that helps us extract just the parts of a list we need, making our code more efficient and readable. So this slide is about how to iterate over each key-value pair in a dictionary. When you use the syntax for key, value in my dict, items, it allows you to go through every pair in the dictionary. Then, by printing key and value, you can see both parts of each pair clearly. It's important to highlight that using items is the way to access both keys and values together, which is really useful when dealing with dictionaries. Now the slide also touches on how this concept extends to lists. When you use enumerate, my list, it gives you pairs of index and value. For example, it yields 0, my list 0, 1, my list 1, and so on. And if you want to start counting from a different number, you can specify a start index with enumerate, like enumerate, my list, start equals 1. This is handy for making your indices more human-friendly or aligning with specific numbering systems. So to sum up, whether you're working with dictionaries or lists, these tools, items, for dictionaries and enumerate, for lists, are essential for looping through data structures while keeping track of both the positions and the content. They help you write more efficient and readable code, which ties back to our overall theme of mastering Python data manipulation. Let's talk about dictionary keys. They must be immutable and hashable. That means if you try to use a mutable object like a list or another dictionary as a key, Python will raise a type error. For example, trying to do D equals a dictionary with a list as a key, like 1, 2. Value is invalid. On the other hand, immutable objects such as strings, numbers, tuples of immutables, or frozen sets can be used as keys. It's important to understand that the hash value of an object should stay the same over its lifetime if it's used as a key. That's why mutable types are not allowed. They can change, which would mess up the dictionary's ability to locate the key-value pair. Now, what happens if you accidentally use a mutable object as a key? Well, Python won't let you do it. It raises a type error. Moving on to iterating through dictionaries, there are a few common patterns. You can use for K and D to iterate over the keys or for V and D values to go through the values. To get both keys and values at once, you can use for K, V, and D items. And since Python 3.7, dictionaries remember the insertion order, which is quite handy. When it comes to removing items, you have options. Using del dh will delete that key-value pair but will raise a key error if the key isn't present. Alternatively, d, pop age, will remove the key and also give you back its value, which is useful if you need it. To clear the entire dictionary, you can use dclear. And if you want to remove and return an arbitrary item, d, pop item, is your go-to. Adding or updating entries is straightforward. Assigning a value to a key like dcity equals London will add that key if it doesn't exist or update it if it does. Accessing values by key is just as simple. dname will give you the value associated with name, but be aware, it raises a key error if the key is missing. To avoid that, you can use getName, which will return none or a default value if specified, making your code more robust. So, in summary, dictionaries map keys to values. Understanding how to add, remove, and access items is fundamental to working efficiently with them. These operations are the backbone of many programming tasks, connecting to the overall theme of data management and organization in Python. In this slide, we're looking at some of the common string operations in Python that can really make your coding more efficient and flexible. First, there's the documentation for Python's string methods. It's a great resource to explore for more options beyond what we cover here. Now, let's consider an example. We define a variable called name with the value Alice, and then we create a greeting using an f-string, which is a very handy way to embed variables directly into strings. So we write greeting equals f hello, name, and that automatically inserts the value of name into the string. Next, we want to find out the length of our greeting, so we use the len function, which returns the number of characters in the string. We print that out, and you'll see the total length displayed. Then, suppose we want to split this greeting into parts, say, separating hello from Alice. We can use the split method, specifying the separator, which in this case is a comma followed by a space. When we print the resulting list, it shows us the individual parts, which can be really useful for processing or extracting information. Now, as an example of different string formatting techniques, besides f-strings, there's the str, format, method and the older % formatting style, which are still used in some codebases. Moving on to formatting methods, Python provides many useful string functions. For instance, supper converts all characters to uppercase s-lower, makes everything lowercase s-strip, removes whitespace from the beginning and end, and s. Replace old, new replaces occurrences of a substring. You also have s, find, sub, which searches for a substring and returns its position, and s, split, sep, which splits the string into a list based on a separator. To join a list of strings back into a single string, you can use s, join list, inserting the string s between each element. It's important to remember that strings in Python are immutable, meaning once created, they can't be changed. So operations like slicing or concatenation actually produce new strings rather than modifying the original. Speaking of slicing, you can access individual characters with indexing, like S0, or get substrings with slices, like S1, 4. This is very powerful for manipulating parts of strings. Lastly, there's repetition, which uses the asterisk operator. For example, be 3 results in a babab. And for concatenation, you can simply use the plus operator to combine strings, such as hello plus world. All these operations make strings incredibly versatile in Python, allowing us to process and manipulate text in many useful ways as part of our overall programming toolkit. So in both cases, using s equals s plus more or LSD equals LSD plus x, the operation creates a new object. For strings, since they are immutable, concatenation results in a brand new string, and we have to reassign s to this new string. It's like making a new copy each time. But when it comes to lists, using plus equals is a bit different. It actually extends the list in place, meaning it doesn't create a new list. Instead, it modifies the existing list directly, which is more efficient. This is similar to what happens with LSD, extend, x. It adds the element directly to the list without making a copy. The key thing to remember is that plus equals behaves differently depending on whether you're working with strings or lists. With strings, it creates a new string, while with lists, it extends the list in place. This distinction is important because it can impact performance and how your data changes during execution. Understanding this helps you write more efficient code and avoid unnecessary copying, especially when working with large data structures or in performance-critical applications. Strings are immutable, which means once a string is created, it cannot be changed. So when we perform slicing on a string, we're not modifying the original string, but instead creating a new one. For example, if I have s equal to ubdef, and I do print s1, 4, it will give me bcd. This slice starts at index 1 and goes up to, but does not include index 4. You can also omit the start index, like in S3, which gives you the first 3 characters, A, B, C. Similarly, if you omit the end index, like in S3, it returns everything from index 3 to the end, which is def. Slicing also works with negative indices, which count from the end of the string backwards. So S-3 retrieves the last 3 characters, def, and if you want to select every second character, you can use S2, which results in ace. Another powerful feature is revering a string. By using S-1, you're stepping through the string backwards, so you get fedgba. Now about the syntax si, j, k, the k here is the step size. It allows you to skip characters in your slice, which is especially useful for patterns or revering strings quickly. Remember si, j gives a substring from index I up to j1, with the default starting point being 0 if you leave it out, and the default ending being the length of the string if you omit j. And just like lists, strings support indexing. Si gives the character at position I, starting from 0. If I is out of range, you'll get an index error. Lastly, the key takeaway is that strings are similar to lists in that they can be sliced and indexed. But keep in mind that strings are immutable, so any slicing creates new strings rather than altering the original. All right, let's look at how we can merge 2 dictionaries in Python. One way is using the update method. For example, if we have D1 with keys X and Y, and D2 with Y and Z, calling D1, update, D2 will add or overwrite keys in D1 with those from D2. So after this operation, D1 will have X, Y, and Z, with Y's value now coming from D2. Another way is to create a new dictionary by unpacking both dictionaries. We can do this with D3 equals **D1, **D2. This creates a new dictionary that combines entries from both, with keys in D2 overwriting those in D1 if there's a conflict. It's a neat, concise way to merge without modifying the originals. And if you're using Python 3.9 or later, there's even a more straightforward method. You can use the pipe operator, like D3 equals D1 D2. This also creates a new dictionary combining both, again with D2's entries taking precedence in case of overlaps. So to sum up, there are several ways to merge dictionaries in Python, each useful depending on whether you want to modify an existing dictionary or create a new one. The key takeaway is understanding how these methods handle key conflicts and choosing the right approach for your needs. So, when it comes to formatting strings with variables in Python, there are several ways to do it, but some are more common and more readable than others. First, there's the old style using the % operator, like s equals name, %s age, %d %name age. This method has been around for a long time, but it's now less common because it can be a bit harder to read and maintain, especially with more complex strings. Next, there's the format method, which is a bit more modern. You can use it with placeholders like s equals name, age. Format name, age, it's straightforward and flexible. You can also use named placeholders like s equals name, n age, a. Format n equals name, a equals age, which makes the code clearer, especially when dealing with multiple variables. But the most recommended way now, especially from Python 3.6 onward, is to use f-strings. To do this, you prefix your string with an f, and then include your variables directly inside curly braces like name equals Bob, age equals 30, s equals f name, age, age. This method is not only more concise but also improves readability because it directly embeds expressions within the string. Overall, using f-strings tends to be the preferred approach because it combines simplicity, clarity, and performance, making your code easier to write and understand. Let's talk about sets and frozen sets. Elements in a set must be hashable, which means you can't put lists or other sets directly inside a set unless you use a frozen set. A frozen set is basically an immutable version of a set, meaning once you create it, you can't change it. This makes it useful as a key in dictionaries or as an element in another set. For example, you can create a frozen set with frozen set 1, 2, 3. Now, a regular set is an unordered collection of unique hashable elements. You can create a set using curly braces like 1, 2, 3, or with the set function. Sets support various operations such as checking membership and performing union, intersection, and difference. For instance, if you have sets A and B gives you the intersection, which are elements common to both. A B gives the union, all elements from both sets. And a B gives the difference, which are elements in A but not in B. These concepts are fundamental because they help us manage collections of data efficiently, especially when we need to test for membership or perform set operations as part of our overall programming approach. Dictionary comprehensions are evaluated eagerly, which means they are computed immediately, and they return new dictionary objects. For example, if you have a dictionary like my dict with keys, A and B and values 1 and 2, you can invert it by swapping keys and values using a comprehension. Inverted equals val. Key for key, val in my dict, items. This creates a new dictionary where the original values become the keys, and the original keys become the values. You can also create a dictionary by, say, mapping numbers to their squares, but only for even numbers. For instance, squares equals x asterisk x for x in range 10 if x%2 equals 0, and this results in a dictionary with keys 0, 2, 4, 6, 8, and their corresponding squares. The general pattern for dictionary comprehensions is similar to list comprehensions. You specify a key expression and a value expression, followed by a for loop over an iterable, optionally including a condition. So, in essence, dictionary comprehensions let you build dictionaries in a concise and readable way, making your code cleaner and more efficient. They're a powerful tool when you want to generate dictionaries quickly and clearly. So let's talk about tuples. As you can see here, we have coords set to the values 10.0 and 20.0. When we unpack this tuple with the line x, y equals coords, we're assigning the first value to x and the second to y now. Tuples are what we call immutable sequences, which means once you create them, you can't change their contents. You define a tuple by separating values with commas, and you can also include parentheses if you like a equals 1, 2, 3, or with parentheses like a equals 1, 2, 3. The key point here is that, unlike lists, tuples don't support operations that modify their contents, such as append or remove. They're often used when you need a fixed collection of items or when a function needs to return multiple values. Because they're immutable, tuples can also be used as keys in dictionaries or as elements of sets, which lists cannot do. Accessing items and slicing a tuple works just like with lists. You can get specific elements or parts of the tuple easily. So, understanding these differences helps you decide when to use a tuple versus a list in your code, especially when you need data integrity or want to ensure the data remains unchanged throughout your program.